So today's plan is to see how we can plan with a model. So we know the model, we want to find the optimal value function and optimal policy. In previous lecture, I talked about like different concepts such as value function for a policy, optimal value function. Also talked about the relation between, say, V star or Q star and the optimal policy, which was connected through the use of greedy policy. Like if we had V star or Q star and computed it their greedy policy, we could get the optimal policy through it. Now, of course, the question is that, well, we have all these nice concepts, but how can we actually find the optimal policy? So here today, the assumption is that we know the MDP. So we know R and P, but the question is how to find these quantities. So this is not still the RL setting. So when I refer to RL setting, I'm talking about the setting that we do not know the dynamics of the environment, P, or we do not know the reward, but the agent, there is an agent that can interact with the environment. So that's the RL setting. So this is kind of like more strict set of assumptions, but still having these type of ideas or algorithms that can compute, say, optimal value function given a model would be important when we want to design RL algorithms. And we see that many of the RL algorithms are kind of like approximate version or sample-based version of these ideas that I'm going to talk about today. So this is kind of going to be, I guess all lectures are important, but this one is especially important because many of the methods are essentially, for the rest of the course, would be essentially approximation of these methods that I talk about here. Okay, so there are different ways to compute, to find pi star. And there is one general way to think about it or categorize them. One is category of value-based methods and the other category of policy search method or direct policy search methods. So what are they? So value-based methods are basically trying to find Q star or V star or approximation of them. And then based on that, compute the greedy policy of approximation of, say, Q star in order to find something that is close to the optimal value function. So that's from, say, Q star, we compute the greedy policy, and then we get pi star. So this is clear, and but there is another kind of category of methods that are, like, say, direct policy search, which are basically type of methods that do not try to estimate or approximate value function explicitly, but just somehow trying to search in the space of policies in some way and find a policy that performs well. So one thing is that there are, like, even these direct policy search methods, they may implicitly compute something similar to value function or value, at least, of a policy. So they evaluate how good the policy is, which would be the value of the policy, but they do not have a kind of explicit representation of the value function in their process. And of course, there are methods that are kind of hybrid in between, that both compute explicitly compute the value function and use that in order to guide their search in the policy space. So this boundary here is kind of very vague. There are many methods that have elements of both them, both value-based approaches and policy search methods. Today, I'm going to talk about mostly value-based methods. And later in the course, we are going to see some methods that are more like hybrid or direct policy search. So that would be, one example would be policy gradient type of methods, which would be more like direct policy search. But then probably some of you might have heard of methods called actor critic. That would be kind of good example for a hybrid method. But here today, I'm just focusing on value-based approaches. Okay, so any question so far? Okay, so maybe just one question from you. Uh, I think in the first lecture, I talked about evolutionary algorithms for searching, uh, for finding a policy. I mean, that's, and I think I said that it's not technically a reinforcement learning algorithm, at least it's not known in the RL community, at least in the, until a few years ago. I mean, people are publishing evolutionary methods as an RL method. But evolutionary methods are basically, I don't know, are you familiar with evolutionary algorithms? Anyone familiar? Okay, so perfect. So do you think it's a value-based method, direct policy search, or hybrid? Okay, we're getting some answers. I mean, my question is vague because you should ask what's exactly, how I exactly implement it. But it seems that, well, I'm getting the policy search, or direct policy search, so that's good. And kind of that's a question, that's the answer I was thinking of, because many of them are like in 30 seconds. Evolutionary methods generate a, you can think of, they can work this way, like you generate a lot of policies, like say randomly, and then run each of them in the environment and compute how well they perform, like compute their performance. And then based on how well they perform, you select those that are performing better and maybe perturb them or kind of do kind of mix them in some way, do a crossover operation on them to get a possibly better policies. So these methods are just have a representation for policy. They implicitly compute something like value because that's a value of a policy, but they do not have a direct representation of the value function. So that's why those methods I would consider as a direct policy search. Yeah, so I guess there's this comment that perhaps fitness implicitly captures something similar to value, and that's right. So fitness would be how well that works, and I guess that's why I'm saying they implicitly have something like value or value function, but not as an explicit representation. But that's exactly kind of the point, that even though they're not explicit, they do something implicit. Okay, so that's the idea. So focus on today is on value-based methods. So let's talk about some terminology, which is going to be kind of used very often. The terminology is that the difference between policy evaluation problem and control problem. So the way that policy evaluation problem is defined, or these are two problems or type of problem. Policy evaluation problem is that, well, you have a policy, say pi here, and we want to compute v pi or q pi. So just that. So I give you a policy that says, for say, for example, robot always move forward. I mean, this is not necessarily a good policy. It might hit a wall if the robot always moves forward. But that's a policy. I want to compute the value function of that policy. And then maybe another policy would be that, I don't know, for the robot, just go 2 meters forward and then randomly choose another direction and go in another direction. So it's kind of like what Roomba vacuum cleaner does. And then that's a policy. So evaluating that policy or computing the value function of that policy is called the policy evaluation problem. So the other problem or kind of terminology is that when I talk about control, it's the problem of finding the optimal value function or optimal policy. So finding V star or Q star is the problem of control. Finding V pi or Q pi is the problem of policy evaluation. This, I guess, the second control might be a bit vague terminology or not clear because people you talk about, say, control theory, which is related at some level, superficial level with this, but it's not exactly this problem. Like finding a problem of control is different from problem of control. But in RL, I guess it is common to mention, say, now we want to solve the problem of control, which means that we want to find a policy or optimal value function or optimal policy. So policy evaluation problem is, you may ask why it's important. The reason is that in many of the other methods, many of the say, planning methods or RL methods use this policy evaluation as kind of intermediate step that is used for finding the optimal policy. So having a module that can compute the value of a policy is going to be useful. And we are going to see one of those methods today. Okay, so I guess the other thing I want to mention is that you also see dynamic programming. So it's, I mean, roughly speaking, kind of dynamic programming are methods that kind of benefit from structure of MDP, such as the kind of the recursive properties that we had in the Bellman equation. And you know from CS, like dynamic programming, you essentially try to decompose a problem to smaller sub-problems and then somehow solve each of the sub-problem and then somehow mix them. So this recursive property of the Bellman equation is somehow capturing that property. That's saying that, say, the value function of this state is related to value function of other states. So if I know the value function of other states, but next state, I can compute the value function of the current state. So this is the structure, kind of structure, dynamic programming structure in MDPs. And several of planning methods and RL methods are essentially trying to, you benefit from this dynamic programming type of approach to find the value function. Okay, any questions so far? Okay, everything is clear, I hope. Okay, so we have policy evaluation and control. Okay, let's think about policy evaluation problem. So as I mentioned, we have an MDP and a policy pi. We want to either compute V pi or Q pi. So this is we are in the discounted setting. So V pi has this definition. It would be discounted value, expected value of discounted rewards. So let's try to think about kind of one approach, maybe a kind of naive approach that tries to compute the value function. Okay, so what we can do. Suppose I want to compute the value of state X. So here. So I want to compute V of X. So what can I do? So let's see what happens to an agent when it is at that state X. It chooses some policy. So suppose a stochastic policy. So chooses action according to these stochastic policies. So it would be A1. It's a random variable. Suppose it has, say, 3 different possibilities, like small a1, a2, and a3. Okay, so from each state, from state X, I have, say, 3 possibilities. And then from state A1, the agent goes to state X2 according to P of X1 and A1, right? So this is good. But then again, if the dynamics is stochastic, then there are a set of possibilities would be like possibly more than 1. So we can get to this state or this state. So maybe I just give you a number. Just state 1 maybe, 7, and state 10. From A2, I might go to different states, like state 3 and state 11. From A3, I may go to again state, say, 3 and state 7. So you see that these states are not necessarily different. So this 3 is the same as this one, and 7 is the same as this one. And then it repeats this procedure again. So for each of them, we have a choice of action again, which would be several actions. And then from each of those actions, we have different possible states in the future. So this is essentially a tree of all possibilities that might happen to the agent. Agent might go through like this path, or it might choose another action, goes through this path, or another path. So there are kind of a lot of different possible futures that might happen to the agent. And for each of those possible paths, we can compute the reward that the agent gets throughout that path, right? Because we know the reward, we know what state it has been in on each of those paths, so we can compute the reward function. So just like a kind of idea, okay, so the expected reward at time t equal to 2 is can be computed like this. So this looks a bit long or complicated, but it is not. So the agent starts from state x. Okay, so it has, I think that's missing. So starts from agent state x, goes to state action, chooses action a with some probability, and then from x and a with some probability goes to x prime. Now we are at the state x prime. With some probability, the agent chooses a prime, and then the reward that it gets would be a function of x prime and a prime. So that would be the reward. So we have this summation over all possible x primes, a primes, and a primes. So I should fix this. So we have this all possible futures. So you see that kind of like big summation. We can compute how much reward the agent gets at states at time equal to 2. And we do this for time equal to 1, 2, 3, 4, up to infinity, and which is essentially moving on this tree, like computing, sorry, I guess the reward we get here at different levels of this tree, and then add all of them. Okay, so what's the problem with this approach? Any answer? Right, so it's intractable. The tree grows very fast. So I guess it's good to think about how fast it grows. Like if you have, say, A actions and X states, how fast the tree can grow. So yeah, think about that. But you see that it's kind of decreasing. The size of the tree grows exponentially with the depth. So this is not tractable. So it's very inefficient. So even though in principle it's possible to do it, we cannot really do it. So this approach does not work. So what can we do? Any suggestion without looking at next slide?
I guess one possible approach is to do Monte Carlo sampling using Monte Carlo based value function estimation.
Okay, that's a good idea. Can you explain how it works? Because I guess we haven't got to that point yet. But what's a high level idea?
So for a particular time step, for example, we are at state st, and then we can do sample different rewards, different trajectories to for example, 100 samples, and then calculate the values, average of those 100 trajectories.
Okay, so yeah, that's a good idea. So the basic idea is that instead of actually expanding this tree, so maybe different color. Instead of expanding the tree with all possible kind of the branches, just randomly follow some of these routes or paths on the tree, and then compute the reward along that path. It is not clear why this method should work, but we will see that it works in some sense. Like we can use it to approximately compute the value function. So, but that's a good idea. But I'm not going to talk about it today. But that's one possibility using Monte Carlo estimation. Any other idea?
I guess another point is that the tree structure, because the Markov decision process is memoryless, the tree structure has a lot of redundant states. We can record that in the memory and then reuse them.
Right, so I guess that would help with the efficiency. Like if we get to the same state, if I know the, say, the value of this state 7 here, I also know the value of this other 7. So that's kind of, I can benefit from that recursive structure. So what I'm going to talk about is a bit different approach. And the key idea is that, well, benefit from the recursive structure of the value function. So this recursive structure is encoded by the Bellman equation. So just let's expand the Bellman equation. So it would be v of x would be equal to reward that we get, reward of following policy pi, plus the probability of going to the next states, x prime, and the value at the next states. So you see that these two values, we have value function here, and we have value function here. And we do not know what the value function is, but we know that if there is a function v that satisfies this equation, that function would be the value of that policy. Right, that we had it because we proved the uniqueness of the fixed point of the Bellman equation. So if you find a v, so if you find a v that satisfies t pi v, then we can conclude that v is v pi. So here I'm just writing the equation for v. If I find a solution of it, that solution would be v pi. So here, what are the unknowns? So we have, okay, so this is defined for all x's. So if it is a discrete problem, so suppose we have n number of states. So we have n equations and the same amount of unknowns, like v of x1 to v of xn. So these are unknowns. So what is special about this equation? Or maybe better to ask, is it a linear equation or nonlinear equation? Okay, so it's a linear equation. Right, and it is more clear to see if I just reorganize the equation to get that, okay, v minus this term is equal to reward. So I know reward, I don't know v's, but v is like appearing here in the form of a linear combination of v's, which with the weight of p of pi of x prime condition on x. And I can write it also more compactly in the form of in a matrix form. So I can write it as I minus gamma p pi times v being equal to this vector of r pi. So I is the identity matrix. So this is the linear system of equation that if I can solve, I can find v pi essentially. So, and you see that this is the same form as a generic linear system of linear equations. So this is like is equal to b. Okay, so if I have such this equation, how can I solve it? Like if you have it, what are your approaches?
So take the inverse of a on both sides and then cancel it on the left-hand side.
Right, yes, so it is, I can compute, right? And if A is invertible, this makes sense. What's the computational cost of doing so? Any idea in chats? Okay. Okay, that's good. I think others should also try to participate. We have like 34, 5 participants. We need more than one. Okay. But the answer is correct. Okay, so so one of the comments is that we had n squared as well, right? So as a method, you mean? Okay, I'm not sure what is the, okay, n cubed is the easy way of taking inverse. There are methods that are more efficient, at least in theory, but I don't know what is the kind of the best method that is found. It's like, I guess it's, at some point it was 2.7 and then it got to 2.3 maybe. But we have something like this. I can't remember the exact thing. So there are methods that that are more efficient than computing the cubic method. So there is a question that how do we know reward? So this is the assumption at the beginning that we know P and R. So that's how we know reward. So there is a question that any assumption to make so that A is not singular. Okay, so that's actually a good point. Like A here, this A that in general, okay, so this step for any matrix A, I mean, we cannot necessarily write this because A might be singular, so it doesn't have an inverse. For the particular A that we have here, is it singular or not? It can be shown that it is not singular. I think I have a result in lecture notes that I'm going to post soon that shows that why this is not singular. But essentially it is because at a very high level, well, the basic idea to prove it is that because of this discount factor gamma here, the eigenvalues of this, okay, remember that if a matrix is singular, it means that there is an eigenvalue that is 0. But in this case, it can be shown that all the eigenvalues of P are within unit circle. So all of them are smaller than 1. They can be complex, but they're all smaller than 1. So if I kind of, this is the complex plane. So this is circle minus j plus j. All eigenvalues of this matrix P are within this unit circle. One of them is here exactly at 1, and the others are at different points. So in general, for any stochastic matrix P. And then because I'm multiplying, when I multiply it by gamma P, all the eigenvalues would be, at most, would be kind of within a unit. So the largest one, which was 1 for, this becomes gamma, and then eigenvalue of probably didn't need this to go into this direction. Eigenvalue of, I mean, we can argue that none of them can become, eigenvalue of I is 1. So if we subtract the largest possible eigenvalue of gamma P, which is gamma, the smallest eigenvalue that we can get would be like 1 minus gamma. And if gamma is smaller than 1, this is always larger than 0. So none of the eigenvalues would be 0, so the matrix is not singular. So I guess that's one way to prove it. Okay, so there's a question that is this because the Bellman operator Lipschitz impact the spectrum? I mean, this is because it's a stochastic matrix, so we can show that stochastic matrix has an eigenvalue, the largest eigenvalue being 1, and then we can go through this procedure. Because we could have an operator that is Lipschitz, but I minus that operator would not be invertible. Just for example, I minus P without gamma, that's not invertible. So even though P might have some Lipschitzness property. Okay, I mean, this is not needed. So here, the idea is that we can solve this as a linear system of equation. But what is the problem with this approach? Or, okay, so maybe that's a very kind of vague question. The problem is that, okay, so if we want to solve that equation, as you already said, we can compute A inverse and then calculate A inverse B. So the computation cost would be something between order of n cubed and n squared. So it would be probably n to the power of 2 point something. But then there are also other methods, linear solvers, that we can use, which are more efficient for computing just the solution. Like in order to compute, say, the solution of linear system equation, we do not need to compute the inverse of A. There are methods that are more somehow directly just go for the solution. And they can be more efficient, especially if we want to have an epsilon accurate solution. Say, we don't want to have an exact solution, but with epsilon accuracy with respect to some norm, then those methods might be actually better than going through computation of the inverse. And also there are solvers that can benefit from structure of matrix A. So I think as a kind of very rough heuristic, if a matrix A is more than few thousand dimensions, like it's like 10,000 by 10,000, computation of inverse is going to be difficult, like on a kind of laptop. I mean, you can compute it, but it's not very fast. But then solving a linear system of equation order of 10,000, that's going to be easy. So this is, okay, so we have a linear system of equation approach. There are different ways to solve it. But in any case, we can do the policy evaluation problem. Okay, so that was policy evaluation. What about the control problem? Like if we want to find a V star such that, which basically means that we want to solve this equation of V is being equal to T star V. And because of the uniqueness of the fixed point of the T star of the Bellman optimality operator, if we find such a V, then V would be V star. The problem here is that, well, if we do it, basically we can write this equation here for any x. We have this system of equation, but here we have this max term, which makes it a nonlinear equation. So this holds for all x as before. But then we have a max, so this is not going to be a linear system of equation anymore. So we cannot compute the inverse, or we cannot use a linear solvers. So we need to somehow use a nonlinear solvers. So in some sense, okay, so the rest of what I'm going to talk about is essentially methods that are trying to solve this equation in a way that are benefiting from structure of the MDP and Bellman equations. So for policy evaluation method, you can think of it as basically we are kind of proposing or inventing methods for solving linear system of equations that are specialized to MDP. And for this control problem, there are methods for solving this nonlinear system of equation that benefit from properties of MDP. Okay, is this clear so far? Okay, okay, so the first method is called value iteration. and you have actually seen it before. So the method works like this. So I first present it for the policy evaluation problem. So we start from some value function v0. So this v0 is a kind of arbitrary function. So it does not necessarily correspond to value of any policy. So I can even choose it to be equal to, say, 0 as a choice. And then we compute a sequence of VKs by iterative application of the Bellman operator for policy. So I take VK, I apply T pi VK to it, which is the equation of, I add reward plus gamma times summation of P times VK in order to get VK plus 1. And when I have VK plus 1, I do it again and again so that I get a sequence. And then, okay, so where have we seen this method? We had seen this one before. Do you remember? Anyone in chat? Okay, yeah, so that's when we talked about contraction mapping and fixed point theorem. Like we talk about for contraction mapping, and in the contraction mapping theorem or Banach fixed point theorem, we said that this is a procedure to get that. And so this is again exactly the same. Because of the contraction property of the Bellman operator, we can use, say, Banach fixed point theorem, and that theorem actually had a kind of algorithm within, like saying how to compute it. And the result of that theorem was that Vk converges to V star when k goes to infinity. So this is good. And we can also have the same procedure for Q pi, with the difference that we need to choose the Bellman operator that is suitable for Q. So takes Q and returns Q. And we can do value iteration for problem of control in order to find V star or Q star. So I again start from some arbitrary value function and then apply one of these equations, depending on which one I want. And then either Vk converges to V star and Qk converges to Q star. Okay, any question? Okay, so everything is clear, right? Okay, so this is value iteration. Let's just look at it a bit more visually. So here I'm showing you how it kind of works. So the x-axis here, so I'm showing 3 different functions here. X-axis is state action space. So x-axis is, so of course this can be high dimensional, but I'm just showing like as one dimension. And y-axis is the value of them. So it's the magnitude of these functions. Okay, so how it works, it looks like this, that we get Qk, and then, so that would be this blue function. We apply the T star to it to get this Qk plus 1. And the red one that I'm showing here is the optimal value function. And if we kind of do this iteratively for several iterations, we get something like these are different T stars. We get Qk plus 1, plus 2, plus 3, and gradually they're converging. They would converge to Q star. So they're getting closer and closer. But maybe another way to think about this. So this is here I'm showing you, this is not the same coordinate system. So this is somehow like space of functions. So each point here is a function here. So this is Q0. I do some computation, I get Q1, Q2, until eventually I converge to Q star. And here what I'm showing, this kind of spiraling behavior, is because showing that these Q functions are gradually getting closer to Q star. So the distance between Q0 and Q star is larger than, say, Q1 and Q star. And if I do the iterations, I get gradually closer and closer. So this is essentially that behavior that we had here, that the norm of them, in infinity norm, gets to 0. Okay, so why value iteration is a simple method. Like, you just apply the Bellman operator, but also it's a very important method. It is one of the fundamental algorithms for planning, and you will see that many of the RL methods are essentially approximation of value iteration, like they're sample-based approximation of it. So for example, in the first lecture, I talked about Q-learning. You can think of Q-learning as one variant of the value iteration, when we just replace samples instead of doing the whole computation of the Bellman operator. Any question about value iteration? Okay, there is one question. Okay, so this is a good question. So I haven't talked about this, but the question is that, is there a trade-off between Jacobi type iteration and Gauss-Seidel iteration, which is updating matrix every time we compute V of X for one state versus doing all of them at once? Or is Gauss-Seidel always better? So what I described for is a type of Jacobi type of iteration, what I described, because I update, I get VK and generate VK plus 1. But there are methods that we can essentially only update one state at a time, and then use the updated value function as kind of a target on the right-hand side, and apply the Bellman operator to it. And that would be, a Gauss-Seidel would be one example of it. So now the question, usually Gauss-Seidel type of methods are converging faster, but I'm not sure if it is always better or not. Yeah, I can't remember if there is any theory that shows that always it should be faster for this value iteration type of problem. But at least often it is better. But that's a good question. Okay. So this is a second method, policy iteration. And so the second method, policy iteration, is a kind of different approach that has basically 2 steps. So what I'm describing here is kind of like a generic form of policy iteration. Policy iteration refers to specific choice of one of these steps. But okay, to make sense what I'm talking about, the generic method is like this. So it's an iterative method, and at each iteration we do 2 steps. One is a policy evaluation, the other is policy improvement. So policy evaluation, we had it like at step K, we have pi k, and then we compute V of pi k or Q of pi k. So this is a policy evaluation problem. And the other step is that it's called policy improvement. So we want to improve the policy. So what does it do? It says that, okay, we need to find a new policy, pi of k plus 1, that is better than pi k. And by better, it means that the value function of pi k plus 1 should be greater or equal to V of pi k. And remember that this was a pointwise. So this kind of entails that V of pi k plus 1 at each state for our state in the state space. So it should be greater or equal than the value of the previous policy. And in one of the states, it should be strict inequality. So at least there should be some, say, x0 such that unless we are converged, unless there is no room for improvements. So this is called policy improvements. And okay, so let's think about how we can do these steps. So policy evaluation. Okay, so we do these things and then we repeat this process. So this is only one iteration of it. So policy evaluation, how can we do policy evaluation? We have already seen it. Okay, so yeah, that's one answer is value iteration. Yes, we can do value iteration for policy evaluation. So exactly this one, right? We can do value iteration, but with a, so here I just choose T of pi k and apply it to Vk for many steps. What other approach do we have? Before value iteration, we talked about another method. Right, we can use linear system of equations to solve it. So this is, I mean, for nonlinear case, it was difficult, but when it was policy evaluation, it's a linear system of equation, so we can solve all of it. Okay, but what about policy improvements? How can we improve the policy? Right, yeah. So I guess one suggestion is use greedy approach. So greedy policy, we can choose the greedy policy to do policy improvement. We see why, but that's a right answer. Okay, so policy evaluation, how we can do policy evaluation and policy improvements. For policy evaluation, it's clear we can either solve a linear system of equation or even perform value iteration for policy evaluation to compute the value of pi k. For policy improvement, one reasonable approach is just choose the greedy policy. So here, the idea is that, okay, after I computed q of pi k, I take the greedy policy, I compute the greedy policy, which is just computing the maximum for each action, and then set that greedy policy as the new policy pi k plus 1. So maybe I have this remark that policy iteration algorithm refers to this specific choice of picking policy as greedy policy. So the way I presented in the previous slide, this slide, is that we should just do policy improvement and find a policy that is somehow better. But in policy iteration specifically refers to when we choose a greedy policy. Okay, so why greedy policy is a proper way to compute an improved policy. So this is kind of like an intuitive idea maybe, or intuitive arguments, but we make it more rigorous later. So the idea here is that, okay, so actually maybe two things. One is there any question about the algorithm itself? Because that's the algorithm. Afterwards, we go and talk about the detail of algorithm. But any question Right, yes. So there's a question that, or there's a comment that the linear system approach would not work if x is continuous. And that's right, because I mean, in theory, you can solve it, not in practice. It would be an infinite dimensional linear system of equations. Still linear, but we can't solve it easily, or unless there's some structure. So actually, I think this is a good point. Like when things are infinite dimensional, like when state space is continuous, there is this important question of how to do any of these things in practice. Like how can we do them on computers? Like how can we even represent a function on a computer? If you want to present a function like say v of x, you can just write it here. So if you have, so even representing v of x when x is, say, even just one-dimensional continuous variable, it is impossible to do it on computer because real line has an uncountably infinite number of points, so we can represent it on a finite computer. But then we do it like we represent functions on computer, and the way that we do it is by approximation. Like as a very crude way, if we have this kind of function, we approximate it by kind of like boxes. And then if we divide, this is like epsilon, then the number of, and suppose the domain is bounded, suppose it's between -1 to +1, I can get 2 epsilon different numbers to represent this function. There might be some error because if epsilon is not very small, then the function might change in the middle of each of these boxes. But if I make epsilon small enough, I can represent it. And of course, this is the kind of the simplest way of approximating a function, and there can be much better ways, which you have probably studied in, say, in your machine learning course. Like machine learning is all about, or a big part of it is about approximating functions. Another part of it is how to deal with the statistical error while approximating it. Right, so if everything is continuous, then we need to do approximation and talk about all these things in approximate way. Okay, so that's good. So maybe we can have a break now. And now is 2:04. Maybe we can start at 2:10, like in 6 minutes almost. Okay, so let's continue with this kind of gaining some intuition about why greedy policy is a proper step or proper way of improving a policy. So this kind of this is at the intuitive level. So suppose we are at the state x. Change to the blue. So the state x, and then we act greedily according to q of pi k. So we have q of pi k, we computed it, we compute the greedy policy. And then we just do it one step. And after that, we follow pi k. So one step greedy policy, at second step, third step, fourth step, we follow the previous policy. So the value of this new policy, what is the value of this new policy? So remember that we had this action value function, which was essentially saying that what is the value of choose follow at the first step, selecting action A, and then afterwards following the policy pi. So based on the description I had here, so this is exactly like the first step, I choose action, greedy action with respect to pi k, and then afterwards I follow pi k. And that would be the value, action value function that I've written here. So what was the greedy policy? greedy policy was computing the argmax of its argument. So I basically have, this is equal to q of pi k at state x, compute, and the choice of action is argmax of q pi k at x and a, right? So notice that this is the same pi k, q of pi k. Both of them are the same. So here I'm choosing the argmax as the action, which means that the action that is selected is a action that maximizes that function. So this is equal to choosing an action that maximizes q pi of x and a. So these two things are the same. Okay, so basically the value of this new policy that I described, one step greedy, the rest pi k, is equal to maximum of q pi k at state x and a. Okay, now what do we do is that let's compare it with the value function of pi k, because that's the value that we get if we follow policy pi k. So v of pi k, and what is v of pi k? It is the action value function where at state x, I choose action according to pi k. So if I choose action according to the policy pi k, the first step, and the second step also I follow pi k, which means that in all steps I'm following pi k, so that would be the v of pi k. So v of pi k at state x is q of pi k x and pi k x. So here I'm writing things for deterministic policies, but if it was stochastic, it wouldn't change much. I just need to change it with some kind of expectation of it. But this is easier to see. Okay, so what we have is that I want to compare this quantity with value function. And also notice that because of this relation that I have, so this is equal to maximum of actual value functions, and maximum is always larger than some specific choice that is selected by pi k, larger or equal. So I have this, combining these two kind of equations or equalities, I get that the value of following greedy policy and then following pi k afterward is greater or equal to value of the previous policy. So, and this is the kind of conclusion. This new policy is equal to or better than pi k at state x. So this is kind of like intuitive level of why this is better. Like by choosing greedy policy only for one step, we are already improving the policy. Of course, when we choose greedy policy for the next step, we are not only choosing greedy policy for one step, but we are following the greedy policy in all following steps. But we can kind of see that from here that if we do it, at each step, we are kind of improving a little bit or some extent, or there's a possibility of improvement. So if we do it in all steps, probably it would be even better. So that's a kind of the intuition. Okay, so let's write the greedy policy iteration in a bit slightly different format. So here, recall we had these two properties. One is that v pi k, recall that v pi k is the unique fixed point of t pi k. So this means that policy evaluation step of policy iteration can be written as this problem, that given pi k, computes q pi k, and we do it by finding a q that satisfies this Bellman equation. And if we find it, that would be if the solution q would be equal to q pi k. So this is from the first step. Here, I guess the difference is that I'm using q here, v up there, but that doesn't matter. Both of them are true. So, okay, so the other step is that what is the greedy policy? So recall that greedy policy is the policy that satisfies this equation. So basically here, what I'm saying here is that, okay, we have Q pi. I compute the Bellman optimality operator to it, and it has a maximization of actions. The greedy policy is choosing the same action as that maximizing action, which means that if I compute the Bellman optimality operator, if I compute the Bellman operator of that greedy policy, it should be exactly the same as T star Q pi K. So this means that if I find a pi K plus 1, that the Bellman operator of it applied to Q pi K is the same as T star Q pi K, then that this pi K plus 1 is going to be the greedy policy, which is basically right is at this policy improvement step. It says that find a pi K plus 1 as a policy that satisfies this thing. Maybe you need to think a little bit about it, that why this is the case, but I think we argued, I had some slides in the previous lecture going through this in a bit more detail. But basic idea is that comparing how the Bellman optimality operator looks like, it has a max over actions, and compare what greedy policy chooses. And you see that both of them are going to be the same. Okay, so there is a question. So the question is, what is the problem of proof? What do you mean? Can you explain a little bit more? Or why don't you use, oh, yeah, okay, good.
You said that the proof, is it like complete or like rigid enough? What was the problem of it?
Here?
The only thing that I can, yeah.
Right.
The only thing I can think of it is that you haven't proved that like it will improve at least one of the states, like strictly, if it's not pi star. That's the only thing I can think of.
Well, I guess the thing that I'm referring to is that the policy I talk about here is that one step I do greedy policy, but after that step, I follow pi K. So it's not in all states I follow in greedy policy. So maybe I write it this way. So like if this is time step, okay, so time is, so time step, greedy policy, if the policy improvement chooses greedy policy, so it has, let's, in policy improvement, we have pi G of Q pi K, first step, the same, the second step, third step, and fourth step. But what I described here, okay, maybe I write it completely, so it would be pi K, and so on and so forth. What I described here is that at first step, I choose Q pi K, but at second step, I choose pi K. So here the argument is the computation that I have done is that I computed the action value function here, which is saying that at the first time step, I choose greedy policy, but at the second, third, and fourth time step, I follow pi K. So this corresponds to this green case. But then actual policy improvement says that not only the first time step, but all other time steps, I follow the greedy policy.
Thanks a lot.
Okay, perfect. So here, yeah, here I haven't. So here, I guess the question is that since inequality is not strict, and I imagine you're referring to this one. Use a different color. So I imagine you're referring to this one. Then, okay, is it possible that it will not converge? So here I haven't proved anything about convergence. I showed that it is not going to be worse essentially and might be actually better, but it might potentially get stuck. But then I'm going to prove that this is going to improve until it gets to the best policy, optimal policy, and afterwards it's not going to improve, of course. But that's for, so this slide is more like an intuition, but not a complete proof. Okay, that's good. Okay, so we have this. Okay, there is a there is a remark here that we also have approximate policy iteration, which is basically saying that each of those steps of policy iteration algorithm can be done approximately. So the policy evaluation might be done approximately. So I only find Q that is approximately equal to T pi K of Q, which then means that Q is not going to be Q pi K. It's something different. It might be close, but it's not the same. And then the other step is that I do not do the policy improvement step exactly. I do not compute the greedy policy exactly, just something different. And then what happens there? So in this case, this pi k plus 1 is not equal to pi greedy policy with respect to pi k. So there are methods for that, approximate policy iteration, and it is useful when we have, say, function approximation, because we cannot do this, solve the policy evaluation problem, for example, exactly. Also, I should mention that for a value iteration, we have approximate value iteration, and which is essentially, we don't do each step of applying the Bellman optimality operator exactly. I think I'm going to talk about approximate value iteration later, and maybe approximate policy iteration, but we'll see. But here, I assume everything is exact. Okay, so what is the result? So we can show that policy iteration algorithm converges to the optimal policy. Also, we can show that if we have a finite MTP, the convergence happens in a finite number of iterations. So it finishes, it terminates. And after that point, we are at the optimal policy. Okay, so to prove it, we have this kind of intermediate result, which is called policy improvement theorem, which basically says that a greedy policy improves the policy, the current policy. So let's go through the statement of the theorem. It says that, okay, suppose for a policy pi and pi prime, it holds that T pi prime of Q pi is equal to T star of Q pi, which basically means that pi prime is the greedy policy with respect to Q pi. So I think we had it a few slides ago. Yeah, so this is essentially, we're talking about this equation, but this is of course in the context of policy iteration. Here I'm talking about just two policy, pi and pi prime. So if pi prime is essentially greedy policy and which means that it satisfies this equation, then we have that Q of pi prime, the value of pi prime, is better than Q of pi, or greater or equal. So it can be the same too. So this is essentially, this theorem kind of make the arguments in the previous one of those previous slides, like a few slides ago, more rigorous. Okay, so any question about the statement of the policy improvement theorem? Is it clear what we want to show? Maybe. Okay. Okay, let's see how we can prove it. Okay, so first of all, the claim is that T star of Q pi is greater or equal to T pi Q pi, which is equal to Q pi. This step is because of this Bellman equation. And this is the claim that we make here. And to see that this is true, just consider any state X and A, and then write T star of Q pi, and write, okay, let's just start from writing T star of pi. So what is T star of Q pi? So it would be a reward function R X and A plus gamma next state, probability of going to next state, and taking maximum over actions of Q pi X prime A prime. So that's T star of Q pi at state X and A. So this maximum of this quantity, Q pi X prime A prime, is always greater or equal than any choice of actions. So maximum of, kind of writing the abstract, FA is greater than equal than any A prime. And here A prime happens to be pi of X prime here. So I just plug it here. So I get that everything, this whole quantity would be larger than reward plus gamma next state of Q pi X prime pi of X prime. And this is T pi of Q pi evaluated at X and A. So we just show that T star Q pi is larger or greater or equal than T pi Q pi. Okay, so what do we have here? So then from the assumption, like assumption that T pi prime Q pi is equal to T star Q pi, we have that T star T pi prime of Q pi, which is equal to T star Q pi, that's going to be greater or equal than T pi Q pi, which is by Bellman equation is equal to Q pi. So we showed this relation. Is it clear? Okay. Okay, so we have shown T pi of Q pi is greater or equal than Q pi. Now we apply T pi prime to both sides of this inequality. So I apply T pi prime here. And use the monotonicity property of the Bellman operator to conclude that, okay, T pi prime of Q pi is greater than or greater or equal than T pi prime Q pi. This is just applying the T pi prime to it, which is from assumption is equal to T star Bellman optimality operator applied to Q pi, which is larger than Q pi, which we showed in the previous slide. So this is like comparing these two. So here I showed that t pi prime applied twice on q pi is greater or equal than q pi. Or maybe I write this other. I think I need it. And that's greater than equal to q pi. And I can repeat this argument for many times to get that for any m, it holds that t pi prime to the power of m, which means that repeating it m times, of q pi is greater or equal than t star q pi greater or equal than q pi. Okay, so is this clear what I'm doing? I have done here.
Can I ask one question?
Sure.
The proof you made in that slide, the previous slide, was simply just t pi prime, not this slide, the wave proof.
Which one?
The one that's like you had just intuition that about.
Okay, right. Yes.
It was exactly specifying that t pi. You don't need to go back there.
Okay.
It was just mentioning that t pi prime.
Mm-hmm.
Q pi is bigger than equal q pi. That was exactly what it's saying, right?
Right, yes. I think so, if I got what you're writing. So you want to say again so I can write it?
Can you go next slide? It's just saying what you wrote of the first line over there. T pi prime of q pi is bigger than equal to
right,
q
yes,
pi.
yes, okay, yes, that's right. So, right. So essentially, I said that if at the first...
This is just one step. This is just one step, right?
One step of it, yeah. Like one step greedy and the rest q pi. This is the same as applying t pi prime, the greedy to q pi. So yes. I just did one step of it.
Yes,
and
yes.
Here I'm going through like from one step to m step.
Yep, great.
Yeah, that's a good observation. Okay, so do you know what should we do next? What we want to prove, let's see what we want to prove is. We want to prove kind of q of pi prime is greater or equal to q pi. So that's what we want. And what we have is this, inequalities. Like trying to see how we can get to that point. I mean, it might not be super obvious. We did something like that at previous steps, or in, I guess, last lecture. But let's see if we can have any ideas here. Okay, so there is an idea of fixed point. Can you explain a bit more? That sounds good to me, but a little bit discussion would be helpful. Maybe I can guide you. Let's see. Okay, take the limit of both sides with m converging to infinity. Okay, that's and m going to infinity. The Spellman operators gives q of pi prime. Yes, that's a. I guess both of these answers are correct. Like they're same thing, different way. So here, the idea is that I let m goes to infinity, and then the left-hand side is t pi prime to the power of m of q pi should converge to q pi. And why is that converging? So the claim, I guess, we need to show that, or the claim would be limit of m going to infinity of t pi prime of. So that's what we have, essentially, these proofs suggest. And this is true because of what property of Bellman operator? Or contraction, exactly. So t pi prime is contraction. So no matter what q function is applied here, when we apply it many times, like infinite times, then it should apply, converge to the Bellman, to the value function of that policy. So I think that's what we are doing here, which is, okay, so we had this equation, take the limit of m going to infinity, as you mentioned. Because of contraction property of the Bellman operator, we get that this left-hand side goes to q pi, and then we combine all these things. Then we get the limit, which is equal to q pi prime, is going to be greater than equal than t star q pi, and greater than q pi. So this is what we wanted to show. And actually what we wanted, I guess, to claim of the theorem is that q pi prime is just greater or equal than q pi. I guess we use this in some other statements, so that's why I'm having it here. So that's the proof. Any question? So here, this proof, we use both monotonicity of Bellman operator and the contraction properties. Okay, so the policy improvement theorem shows that if we are given some policy pi k, the new policy, the greedy policy, pi k plus 1, is at least as good as the previous one. It doesn't show that it should converge to the optimal policy. It's just not worse. But we can actually show that policy iteration algorithm converges to an optimal policy, and we prove it. And if the state space or the MDP is finite, like the number of state actions is finite, this happens in a finite number of iterations. Okay, so let's try to, well, let's state this policy iteration algorithm's convergence. So this theorem has several statements. So, okay, so let's go through it. Like, say we start from policy iteration algorithm and generate a sequence of pi k's. So let pi k be the sequence generated by the algorithm. So for all k, first we have v of pi k plus 1 is greater or equal than v pi k. So that's a first statement. So with the equality, this becomes equal only if and only if v pi k is the optimal value function. So policies, we can think of it like this, that so this is v pi k, and then v pi k plus 1, and then it kind of like higher means greater, pi k plus 2, and so on, until we get to v star. And if one of these pi k's gets to exactly the same point, like I can't put it exactly, but suppose this green line is the same. So if some v pi k prime here is exactly v star, then the result is that pi k is optimal policy. Okay, so that's another statement. The other is that we have a convergence, like v of pi k, the distance between v of pi k and v star goes to 0 in supremum norm. And so the other part of the theorem is that if the set of policies is finite, the policy iteration algorithm converges in a finite number of iterations. So that's the theorem, multiple parts. But the idea is that it improves until it cannot improve. And when it cannot improve, it is converged to optimal policy. So, and the basic idea, I mean, the proof is, it's not super complicated, but it has several steps. But the basic idea is that we either can strictly improve the policy, or if we cannot, we are already at the optimal policy. So either that, so in the policy improvement theorem, we only could show that it is improving, or it is not worse, it's greater or equal. Here we show that it is actually strictly better unless we are done. Okay, so the first step of the proof is, okay, so I broke down the different claims. One is that we want to prove that v of pi k plus 1 is greater or equal than v of pi k. But this is exactly the policy improvement theorem. So again, this is policy improvement theorem, which basically says that v of pi k plus 1 is greater or equal to pi k. That's greater equality, it's not strict equality. The other is that suppose v of pi k plus 1 and v of pi k are the same. So the value functions are not changing at two different iterations. Then the result is saying that, or the claim is that v of pi k should be already the optimal value function. Okay, suppose instead of having a strict inequality in here, we have an equality. So we get v of pi k plus 1 equal to v pi k. So we apply t pi k plus 1 on both sides of this. So t pi k plus 1, t pi k plus 1. So I've written it here. So t pi k plus 1 applied to v pi k is equal to t pi k plus 1 applied to v pi k, v of pi k plus 1. Also, the other thing is that what is v pi k plus 1? It's a greedy policy. So it satisfies this equation that t of pi k plus 1 applied to v pi k is the same as the Bellman optimality operator being applied to v pi k. So this means that, okay, just substitute it. So here, t pi k plus 1 of v pi k plus 1. So here I'm using this identity, would be equal to t star v pi k, which is t star v pi k plus 1. And this step is because by assumption, these two things are the same at that step. So v pi k plus 1 is equal to v pi k. So I could do this last step. Okay, so let's see. So I just bring back what I want from the previous slide. So t of pi k plus 1 applied to v of pi k plus 1 is equal to t star v pi k plus 1. Okay, and as v pi k plus 1 is the value function of pi k plus 1, so it should satisfy its Bellman equation. So t pi k plus 1, v pi k plus 1, it should be equal to v pi k plus 1. Right, so this means that this quantity, which is equal to this left-hand side, can be replaced by v pi k plus 1, which is exactly what I'm doing here. So I get that v pi k plus 1 is equal to t star v pi k plus 1, which just comes from this equality. Okay, I mean, a few steps you have to go through it to see like what has been substituted with what, but we got to the point that we got a v pi k plus 1 is equal to t star v pi k plus 1, which means that v pi k plus 1 is a fixed point of the Bellman optimality operator. So we get to the point that we get a value function for a policy that is the fixed point of Bellman optimality operator. But then the Bellman optimality operator only has one fixed point, and that fixed point is the optimal value function. So that's equal to V star. So this means that V pi k plus 1 should be equal to V star, the optimal value function. So basically, here we started from the point that two value functions and two consecutive iterations are the same, and get to the point that if we get to that point, that value function should be already the optimal value function. So the other side, the other direction is perhaps more direct. Suppose V pi k is equal to V star, so it's optimal value function. Then we want to show that V pi k plus 1 is equal to V pi k. So if we get to a point that is optimal value function, the next step stays the same and equal to optimal value function. So this goes like this. Suppose that if we have the assumption of this part is that V pi k plus 1 is equal to V star, optimal value function. So P pi of k, the policy k, should be already the optimal policy, or should be an optimal policy. So, and then the greedy policy of V pi k is the greedy policy of the optimal value function, and the greedy policy of the optimal value function is optimal policy. So if we have a greedy policy of V star, that gives us a pi star. So the value of it then should be, so this would be our so Vk plus 1 should be equal to V star, should be equal to V pi k. So essentially, when we get to the optimal value function, nothing changes. Like the greedy policy at each step would be just the optimal policy. Okay, so that's this part of theorem. So that we have V pi k plus 1 is greater or equal, and if it's equal, when we get to the optimal value function. Now we want to show that this is actually the distances between value function getting smaller. Okay, so from a few slides ago, we had that q pi k plus 1 is greater or equal than t star of q pi k, which is greater or equal than q of pi k. And then, so I can replace q pi k by the relation with q of pi k minus 1. So I basically have that q pi k plus 1 is greater or equal than t star q pi k. So that's this part. And now I'll just expand this. Just apply kind of the same argument here and get that this is greater or equal than t star applied to t star q pi k minus 1. And I can do that because of monotonicity of the Bellman optimality operator. And if I do it multiple times, I get to the point that it would be t star Bellman optimality operator applied k times to q of pi 0. So I'm connecting q of pi k plus 1 to q of pi 0. And the connection is that through this k times application of t star. Okay, so that's one fact. The other fact that we need is that the value of any policy is smaller than optimal value function. So we have q pi is smaller than q star, or it can be equal to, for any policy, including all the policy pi k's generated during the policy iteration algorithm. So we are kind of sandwiching q pi k plus 1 from both left side and right side, or upper bound and lower bound. From the lower bound, or from upper bound, we have that q star should be greater or equal to q pi k plus 1. This is essentially coming from here. And then the lower bound would be that q pi k plus 1 is greater than equal than t star of pi k, which comes from this step of the proof. So essentially, what we have is, maybe if I can. So this is q star. This is, say, q of pi 0. We apply t operator k times to get to this point, which is t star k of q pi 0. And then what we have here so that would be q of pi k plus 1 would be this kind of black line between them. So from upper bound, q pi's optimal value function. From lower bound, q pi 0, that after k application of the Bellman optimality operator to it. Is this clear? Okay. So we just try to now show that, argue that when k goes to infinity, then the distance between both sides of that sandwiching thing goes to 0. So by the contraction property of the Bellman operator, the distance between t star k q pi 0 and q star goes to 0. That's because of contraction property. And also, I guess we can argue that the distance between q pi k plus 1 and optimal value function is smaller than the distance between its lower bound and upper bounds, which is exactly what we have here. Okay, so this goes to 0 by this step. So q pi k plus 1 and q star should also go to 0. The upper bound of this going to 0, so this should go to 0. So basically, we have proved that the limit of k going to infinity of q pi k, the distance of it with q star should go to 0. So that's the kind of what we wanted to show here, that q or v goes to 0. Okay, so I guess the other step that remains to be done is that if the set of policies is finite, we converge in a finite number of iterations. So the idea here is that if the number of policies is finite, the number of times that we can have a strict inequality here, the number of times that this can be q pi k plus 1 going to p q pi k is going to be finite, being strictly greater than q pi k. Because at each step, we are improving one policy, and there are finite number of policies, so which means that at two different iterations, these two policies are not the same, they're different, because otherwise their value would be the same. Because the value is different, so the policies should be different, but then at each iteration that we have strict inequality, one of those policies would basically, we consume one of the policies. And we have finite number of policies, or if we have finite number of policies, then this number of iterations would be finite. Okay. So that's kind of the end of the proof. So some remarks. So some remarks, one remark is that if policy iteration algorithm converges to optimal policy in a finite number of iterations when we have a finite number of policies. So when do we have a finite number of policies? When state and action space is finite. So if we have X is finite and A is finite, then the number of policies would be finite. And you can argue that the number of policies, and here we are talking about deterministic policies, would be the number of actions to the power of number of states, which is going to be very large. Like if we have a, say, grid board, 10 by 10 grid board with 4 actions, this would be 4 to the power of 100 policies, which is like order of 10 to the power of 60. So it says that we prove that policy iteration converges in a finite number of times, but that finite number of times can be 10 to the power of 60, which is probably not very good. But then in practice, if you run policy iteration algorithm, you see that actually converges very fast, like in a few iterations, like 5, 10, 20 iterations for these problems. So it wouldn't even take thousands of iterations. So policy iteration algorithm is actually converging very fast in practice, which suggests that maybe the analysis that we had is very crude. So it's a very just a convergence proof, but doesn't provide a good rates for convergence. So this is interesting. So I'm going a few minutes over time. Want to finish this slide because this lecture because we are almost done. One comment here that is interesting is that it took a while for people to. Are you talking, Farahmand? Oh, okay. So it took a while before people find a better result, like proving that actually policy iteration algorithm converges in finite number of time, but that finite being reasonable took a long time. So it was proven around 2011, 13, 16, something like that, just less than 10 years ago, which is interesting because policy iteration algorithm is one of the older algorithm. I can't remember when it was, like, I guess it was Howard who introduced it, I think in 50s maybe, or 60s. I think it was 50s. So the result, okay, so improved result is this, that we can show that policy iteration algorithm actually converges in an order of X number of states times number of actions divided by 1 minus gamma, discount factor, times some term that is like log of 1 divided by 1 minus gamma. So this is much, much smaller. Like if we had the previous iteration, I guess previous example, we had 100 states times 4 actions times some gamma. I don't know what gamma is. Suppose it's 0.99 of log of that. It would be, what's 400 times 100. So 40,000, much better. And practice probably it solves it all in 5, 10 iterations. I am not going through the proof of this, but you will see it in the lecture notes that I'm going to post, or look, you can look at also the these papers. So the proof that I'm using is from this Bruno Scherer's paper in 2016. Okay, so I have a few more slides. So I talked about value iteration. I talked about policy iteration. There is another way for finding the optimal value function for NDPs. based on linear programming. So we can find V star by solving a linear program. And this is kind of interesting because it's very different from the other iterative algorithms. We write it as a kind of constraint optimization. This algorithm, I guess linear programming is less commonly used, especially in the RL context when we have samples, even though there have been some, like enough research how to do it. But maybe it is not as easy to do it with deep neural network. So maybe that's why they are not very common. Or maybe it is possible to do with deep neural network. So that might be a good project to do it. I don't know if it's feasible or not. So it's good to search first whether anyone has done it. And if not, think a little bit to see if it is possible. But anyway, so I'm just giving the description for the case that everything is exact. So the basic idea is like this. Suppose all value functions that satisfies this inequality, that v is greater or equal than t star v. So this is a set of functions that I here denote by C, capital C. So here notice that this is not referring to any particular value function for any particular policy. These are just functions. But these functions satisfies this inequality. So what is the significance of it? They have some interesting property, which we use in order to derive this linear programming formulation. What is the property? So for any v in that space, we can apply the Bellman optimality operator to it once. Based on monotonicity property, we get a result like this. So I have this, I apply t star to both sides to get t star v is greater than equal to t star of v, or t star to the power of 2 of v. So I showed that v is also greater or equal than this. So if we start from C, we have that. We also have this property too. And if we do it multiple times, for any m, we get that v is greater or equal to t star to the power of n of v. Okay, so this is interesting. And probably from what you've seen before, we can, when we are doing this, we are usually taking the limit of m going to infinity to get to some quantity. So what is the quantity here? So here the Bellman operator is t star. If I let the limit of m going to infinity, so as m going to infinity, this converges to what? tv star, right? So I have that v is greater for any v in that space C. V is also going to be greater or equal to v star. Okay, so what is the interpretation of it? So any v in that set essentially is greater or equal than the optimal value function. Right, so one interpretation is for any v in that C, that v is going to be lower bounded by v star, or just changing that direction of talking about it, is that v star is a function in C, because also v star is going to be in C too, right? Because it satisfies with equality. Like, so v star also belongs to C. So v star is a function in C that is smaller or equal to any other function in C. And smaller or equal is pointwise as usual. Like for any state, it is always smaller. Okay, so what is the idea? Now we have a C, so set of value functions had this property. And then we know that v star is the function that is smaller than any of them. but still it is within that C. So how can we find that? Any idea? So maybe I should draw some sets. Suppose this is the set of C's. So this is C. Maybe that's not actually. Yeah, so I guess this would be better. So this is set C, and all points here satisfies that inequality. But V star is the point that is smaller than any other points here, which means that it should be here. Like if I compare it point-wise, for any other V here, V star is going to be smaller than V. So that's kind of like geometric intuition of it. We are in this set C, and then we find a point that is smaller than any other point there. Okay, so how we can do it? We can do it by choosing a strictly positive vector mu. So vector mu should be positive, and it should have the same dimension as a value function. So it should be x dimensional. So if mu should belong to R of x. So what we want to find is that based on the kind of geometric argument, find a minimum of V in that C such that mu transpose V is smallest. Here, we need a little bit of argument why this is exactly what we want, because what I said is that we want to find a V such V star such that it is smaller than any other V in that sense. So I want to find kind of like minimize for all x's in some sense. So it should be true for, so maybe this is not accurate, so I erase it. But basically we want to find a V point.
One option is U.S. Consulate General Toronto. Visa services on Simcoe Street. Does that one set?
No. Okay, I can go away. Okay, that was funny. Okay, essentially we want to find something that is smaller than any other one, and we can do it by finding a mu transpose V, that the sum of all V's, all components of that V, so that is essentially writing mu x V of x. If the sum of all of them is smallest as possible, then what we want is actually going to be satisfied. And we can argue that this is true. But essentially, we find this constraint optimization, which if we write it in this form, like if we want to expand it, we get that we want to find a minimum V such that the objective is minimized and the constraints that we had in previous slide, like this constraint of belonging to C, is satisfied. So we want that V to be greater or equal than T star V for all state x's. So this is a linear objective, but nonlinear constraints because of the T star, it's a max in it. But we can convert that nonlinearity to linearity. Just look at one of the states. So the constraint is that V of x should be larger than maximum over actions of all these ones. So you can, we can show that. I mean, I guess you need to convince yourself that this is equivalent of V of x being greater or equal to Rxa plus everything for all the actions A. So if you have, say, 10 actions, if it is greater than or equal the first action, second action, up to 10th action, it is the same as saying that we want v of x to be greater or equal than maximum of those terms. The question. So I get the question, I guess, is previous slide. So mu here is the initial state. The question is that is mu here's the initial state distribution, and then there is an answer that I think it's any strictly positive vector. So that's true. So at this level, we don't have an interpretation of it as initial state distribution. So it can be any strictly positive vector, which do not even need to be initial probability. Like it doesn't need to sum to 1, but you can make it a probability too. Yeah, so any strict vector, strictly positive vector is sufficient. Okay, here we got to the point that the constraints became linear constraints. So let's write everything again. So we have a minimum of mu transpose V for any mu for constraints that are now linear constraints for all state x and a's. So this is a linear program with x times a type constraints, which is interesting because then we can solve a linear programming approach or use a linear program solver in order to find a V star. I guess one comment is that if the number of state action spaces, number of state and actions is large, then the number of constraints also grow. Like if you have, say, 100 states for action, that's 400 constraints. That's not very large. But if it's much larger, like millions, then that's difficult. And I guess even more interesting case is the case that we have a continuous problem, continuous state problem or continuous action. Then in that case, the number of constraints would be infinity, uncountably infinity. So it is not trivial how we can solve it. And there are a lot of research there, so it is not, we don't know how to do it. There is a function approximation version of linear programming. So I guess that's one thing. I don't think I'm going to talk about it any further during this course. I guess the other interesting observation is linear programming, solving it using a simplex method can be interpreted as one version of policy iteration. And actually the proof of conversion of policy iteration in 2011, I think by Yi, was for this version of policy iteration based on linear programming approach, if I remember correctly. So that's interesting, like simplex linear programming is one version of policy iteration algorithm. Okay, let's summarize. So we have 3 methods for computing the value function for policy or optimal value function. So value iteration was for both policy evaluation and policy iteration. But for optimal policy computation of the optimal value function, we had value iteration, we had policy iteration, and we had linear programming. And then conversion of value iteration, we got it from a result from last lecture, the Banach fixed point theorem. But we went through the proof of policy iteration, the conversion of policy iteration algorithm. We had this step of policy improvement and proved that it works, and also the whole proof of convergence. And I know the proof of convergence is not something that, I mean, had a lot of notations, so we had to be careful which pi k we are talking about, but it was simple. Maybe too many steps, but it wasn't very complicated. But then that proof is not going to be, like the convergence rate was bad, like it could converge very slowly or show that it converges slowly. But then there is this faster proof that you will see in the lecture notes, which is not too much more complicated. I think it's still, we could cover it, but probably took half an hour. which is interesting. Also, I guess the last comment is that all these methods have variants for reinforcement learning, for value iteration, policy iteration, and linear programming. And we are going to see at least some of those variants in next lecture or in the next few lectures. I think that's all. It was a bit over time, 20 minutes. If you have any question,